much as illustrated medieval manuscripts in terms of its aesthetic beauty. And Elias is also author and the main contributor of Complex Beauties, which is a series of calendars featuring face portraits and various special functions. Well, without further ado, we'll let Elias talk about the Riemann-Hilbert problem.
Thank you so much. So first of all, I'd like to thank the organizers for inviting me to this nice program and the Isaac Newton Institute for Financial Support and Hospitality. So I will talk about a very old boundary value problem which goes back to Riemann thesis. This is kind of a modern version of it. This is a circle packing Riemann-Hilbert problem. I will not talk about this, it's just for entertainment, so for your entertainment, and I will cancel it hopefully right now. Okay. And start with the talk. Here you see an outline. I will talk on some history of the problem because this is quite interesting. Then I will describe the geometric setting of the problem. And then we come to some results. And in the second part of the lecture, I will speak about two applications. I'm always interested in getting more applications, and I hope that you can contribute to this somehow. So we start at the very beginning in 1851 when Bernhard Riemann published his thesis, Grundlagen für eine allgemeine Theorie der Funktionen einer veränderlichen komplexen Größe.
Can you translate for us?
Yes, I mean, this means foundation of a general theory, say, of complex analysis of functions of a complex variable. So this paper is well known and famous because it is the origin of Riemann's mapping theorem. What is less well known is that Riemann himself considered conformal mapping just as a simple example to illustrate a more general type of boundary value problems. And this is what the talk will be about, these Riemann-Hilbert problems. So this general interest is to find reasonable boundary conditions, whatever this means, which can be posed on polymorphic or say analytic functions in some domain. And this is kind of a huge project, namely to find complex functions from conditions under values at the boundary and, how Riemann says, at discontinuities of the function. It's not completely clear what he means by discontinuities. So let's start with some simple examples as Riemann did. He said if we decompose the function in real and imaginary part, then we can prescribe real part more or less arbitrarily along the boundary, and this determines the imaginary part more or less uniquely. And in fact, the solution can be given explicitly by Schwarz integrals formula. There is an additional free constant, maybe you keep this in mind, which is not determined by the boundary condition alone. So and then he goes on and gives some heuristic arguments, no real proofs, but he just talks about this thing and he comes up with the following conclusion. Oops. The conditions which were found to be necessary and sufficient, necessary is here, sufficient is there, are related to the value of the function at boundary points. Namely, they give one equation for every boundary point. Okay? And this is what I call a Riemann-Hilbert boundary value problem. You will see why I call this a Riemann-Hilbert boundary value problem and not just a Riemann-Hilbert problem. In fact, there's a confusion with the names. And I try to distinguish these. Most or almost all what I will tell you today is about Riemann-Hilbert boundary value problems. This is not what you might expect from the talk, because most of you are working on Riemann-Hilbert transmission problems in my terminology. So here we have the setting. We are looking for holomorphic functions W in the complex unit disk state, which are continuous on the closure of the disk, such that at the boundary point, here we have the T along the unit circle, such a nonlinear boundary condition is satisfied. Here this function f is a given function. T is on the unit circle. The second argument of f is in the complex plane, and it is real valued. So we impose one real condition. We will see that this makes sense. And this is what Riemann said. Now, it's always interesting to read the original sources. Those of you who understand German may enjoy this. You see, there are no formulas, except some very small things. And he makes quite general and quite vague statements. Now probably I have a difficulty. Yeah, this turns up. I think you still can see this blackboard below here. While you are trying to understand what Riemann says, I can give an explanation. How general these problems could be. First of all, he says it is not necessarily so that the boundary condition is just related to one boundary point. Such a condition we have on the left side. We have the limit of the function at the boundary point and the nonlinear condition at each point. But we can also consider problems where this boundary point belongs in some sense or has two sides, an upper and a lower side, say. This is included. And then we have a coupling of the boundary values from above and from below. A nonlinear problem of this type would look like this. This is what I call a Riemann-Hilbert transmission problem, because it's a condition which relates the two limits from both sides. And of course, this is what you think usually goes with the name Riemann-Hilbert problem. This is a linear version of it, so we have a minus function which is g times a plus function plus something which is given. So this is also included. But Riemann goes further. He says it need not be just one point t. We can also have several points. This is t, and this is a second point which is somehow related to this point. Then we get a condition of this type, which sometimes is called the Riemann-Hilbert problem with shift. A very special case of this is the so-called conformal welding problem. Here we have two functions living on the Riemann sphere, one on the upper half, on the upper hemisphere, the second one on the lower hemisphere, and they are coupled across the equator by such a condition. And we can go to multiply connected domains, and you can go on and go on and go on. So this is an incredibly large field, and only the beginning of this field is explored, I would say. Okay. So, 3 comments about Riemann's paper. First of all, it is important that he emphasizes the geometric aspects of the problem. He says we have a manifold of one dimension for each boundary value. Yeah, this we have seen. His statements are rather vague. There are no proofs, no theorems, and the complete section only contains one formula. Here, there's everything in words. This may have been the reason why this Riemann-Hilbert problem has been somehow overlooked by all biographers of Riemann. I'm not aware of a single biography of Riemann which even mentions the problem. And first, or most importantly, Riemann had the right intuition. He does not only say this is a reasonable boundary value problem, but he also says, well, this boundary condition is not all what we need. At least in some cases, we also have to allow additional free parameters, and we may need additional equations which specify something. This is all he has seen, which is, to me, almost unbelievable. Oops. Yeah, and see, I made this comment here. If you read Riemann, then you really get the feeling that mathematics is just a footnote to Bernhard Riemann. This is not my idea to say. I like it. So now to his example. He says, now let's be more specific. We consider a special example, namely conformal mapping. And his approach to conformal mapping is a bit strange to us nowadays, because he starts with the boundary correspondence. We all know that this is a subtle thing, and it is not completely clear. I mean, it is clear, but it's not simple to characterize conformal mappings by the boundary correspondence. But he does not worry about this, and he says, this is a Riemann-Hilbert problem, I say, where these, maybe I can show it. No. This goes wrong. That's it. Where all boundary conditions are the same for every boundary point, which in some sense expresses the fact that the boundary of the domain of the unit disk is mapped onto the boundary of the range domain. So, but we immediately see that this boundary condition alone is not a complete characterization of conformal mappings. Of course, we have trivial solutions, all constant functions which map just to a single boundary point are also solutions. And we have solutions which give multiple coverings of the range domain. This can be seen best when we consider a very simple, now a nonlinear Riemann-Hilbert problem, where we are looking for all polymorphic and at the moment continuous functions in the disk which have modulus 1 on the boundary. So this is the complete set of solutions. These are the finite Plaschke products. They have zeros in the unit disk. They can be prescribed arbitrarily, and there's an unimodular constant in front. These are exactly the solutions of this Riemann-Hilbert problem, which extend continuously to the closure of the disk. Now, we can enlarge the class of admitted solutions, which changes things dramatically. If we are looking for bounded holomorphic functions, this is, in a sense, the most natural class for this type of boundary value problems, then the solution set consists of all inner functions. The inner functions are just characterized by this property. And the inner functions comprise infinite Plaschke products and also so-called singular inner functions. So if you don't know what a singular inner function is, do not worry about this. This is just a specific class of, say, wild solutions to this boundary value problem here. Let's generalize this a bit. We can prescribe the radius of the boundary values arbitrarily. more or less arbitrary. Then we get a standard class of solutions, namely those solutions without zeros in the disk are the so-called outer functions. They can be expressed as, by this integral formula. Here we have the logarithm of this r. This is the standard solution of this problem corresponding to the solution 1 in the former example, constant 1, and or constant c. We have with this. So now let's combine the two problems somehow. First of all, the general solution is then obtained by multiplying such an outer function by an arbitrary inner function. So we have a very large class of solutions. And combining these two examples, we can relate this to a famous result. This is the inner-outer factorization, which goes back to Arne Böhring, which says that any bounded holomorphic function is a product of an inner and outer function. So any function can somehow represent it as a solution of two more or less independent nonlinear Riemann-Hilbert problems. So when we prescribe the modulus, then it's a natural question also to prescribe the argument. This leads more or less, it's not equivalent, to the homogeneous linear Riemann-Hilbert problem. This is the usual way to write such a problem. Here we have a given function small f, and this w, as always, is the unknown function we are looking for. If we replace the right-hand side by the c, then we get the general scalar. I'm only talking about scalar Riemann-Hilbert problems, the scalar linear Riemann-Hilbert problem. And this is already an interesting object. This function, which is the main ingredient of the problem, f, this is called the symbol of the problem, and its topological properties, global topological property of this symbol, namely the winding number of the image curve of the unit circle, is crucial for the solvability properties of this linear Riemann-Hilbert problem. So let me briefly show some milestones in the history of these linear Riemann-Hilbert problems. I mean, Riemann stated a very general problem. Hilbert was the first, was not the first, but he is the next one whom I would like to mention. Hilbert gave first solutions to this linear Riemann-Hilbert problem. What is interesting is that he introduced the Hilbert transform, the Hilbert operator in this paper. So the problem was also the source of some interesting results and mathematical objects. So what he did is to reduce the boundary value problem to a singular integral equation, and then he somehow reduced the singularity, treated it as a Fredholm integral equation. But there is a well-known error in Hilbert's paper, namely he made a mistake which led him to miss the index. So Hilbert did not discover the solvability of the problem depends significantly on the index and the winding number of this function. And this was pointed out almost 20 years later by Fritz Noether. And Fritz Noether was the first who treated this problem appropriately, I would say. He introduced the index. This is really the birthplace. His paper is the birthplace of the concept of index, which has been later generalized to become a real big theory. And Noether gave a complete formal solution. When I say formal, this means he did not work in spaces, in function spaces. This was done again 10 or 15 years later, independently, more or less by three Soviet mathematicians, Musrelishvili, Gapow, and Kvekwa, especially Musrelishvili's book is still in use. They worked in spaces of further continuous functions and gave a complete solution. Then this was extended in 1960 by a paper of Simonenko, who gave a complete solution for piecewise continuous coefficients and right-hand sides in Hardy space, right-hand side in L2 spaces. And here's a summary. So we introduced the Hardy space. You certainly know what it is. And then we know that functions in this Hardy space, it can be done for HP, but I just do it for H2. These functions have boundary values in the sense of non-tangential limits. Oops. What is this? Oh. Almost everywhere on the unit circle, and the boundary function belongs to LP. So the problem may be stated consistently in these HPLP spaces or H2L2 spaces, and we can introduce a Riemann-Hilbert operator which maps the W to the imaginary part of F bar times W. And the main result is this operator is Fredholm. In fact, it would be better to say Noether, because Fredholm had no index. It was Noether who introduced the index. And the dimension of the kernel and the codimension of the range is given by these formulas, where this kappa is the winding number of the symbol F about the origin. So if this kappa is positive, then we have a non-trivial kernel, and if it's negative, the operator is not surjective, so we need additional conditions on the right-hand side to get a solution. So here's a short outline of what was going on for nonlinear Riemann-Hilbert problem. I think I'm running a bit out of time, so I will just be very brief. Here, this is a milestone in 1972. Alexander Schneermann. At this time he was in Moscow, now he is in Tel Aviv. He really read Riemann's thesis and he found the original setting, the geometric setting, and he gave a very important contribution which I will explain later. Yeah, okay. So, now about this setting. On the left-hand side, you see an attempt to translate Riemann's writings. No, on the right-hand side, you see an attempt to translate the left-hand side. And I think the best way to state this problem is in this geometric way, namely we have a unit disk, and on the boundary of the unit disk we have points t, and with each boundary point there's an associated target curve called nt. And the condition tells us that the w at the point t should be on the corresponding target curve. Okay? So now Schneermann came back to this setting, and so we can write this boundary condition in this form which changes nothing. But in fact, I think looking at the problem from a geometric point of view changes something. To get other ideas. Okay, now if we draw all these target curves in the complex plane, so we get a tangle of curves and it's not clear what is what, it's better to lift everything up. So we go in, say, 3 dimensions. So there's a base point or as a baseline. This is the unit circle T here. And on top of it we have fibers complex planes, and every target. I don't know what's the reason.
And there is a connection problem with the laptop.
I think the network needs some sound.
Maybe.
Yeah.
Yeah. Okay, let's see. So we lift everything up, and we have the fibers here shown as planes, and the target curves are just the intersection of these planes with this object, which I call a target manifold. So the problem is completely encoded in this target manifold. So we can really see it. This is the advantage. What about solutions? Of course, any solution is already determined by its boundary function, and we can consider the graph of this boundary function here, which is a line on this target manifold. Okay? So now, of course, we see immediately that there are different geometric types of target manifolds. A very rough classification says we can have closed target curves, then the manifold is torus-like, or we can have open target curve as for the linear Riemann-Hilbert problem. Then we get a band-like target manifold. You see two such examples here. First of all, let's look at linear Riemann-Hilbert problems with, in this new geometric setting. Here the target lines are straight lines, and the target manifold looks like this. And we see it has a global characteristic, which is kind of a twisting number. And this twisting number is exactly the winding number of the symbol F. Okay, so we have a problem with index 0 here, and the problem with index 1 on the right hand side. Orientation is, of course, important. So now what about solutions? If we work with say Muskanishvili's conditions that we have in Hölder continuous F, then we have a one-parametric family of solutions, and they are arranged very nicely on this target manifold. The traces of solution do not intersect each other, and they cover this target manifold in a schlicht manner. If we would assume that this symbol is just continuous, this would be wrong already. There are examples where this does not hold. So, if we go back for a minute, then you see here we have index 0 and here we have index 1. Why don't we have something in between? It also makes sense to consider target manifolds which are non-orientable. And the other way around, you may wonder why this kernel dimension jumps by 2. Why doesn't it jump by 1? Wouldn't it be better? Of course, it jumps by 1 if we also admit non-orientable target manifolds.
What if the index is negative?
If the index is negative, then you have at most one solution. And this solution exists when the right-hand side satisfies additional conditions. And you get the more conditions, the more negative the index is.
But what is the geometric interpretation of
Yeah, then you have just one line on the target manifold or no line at all. Okay. So these non-orientable problems fit very nicely into the gaps which we have. And this is already an advantage of this geometric point of view. You see that something is missing. And this is the result expressed in a formal way. The best thing is, in fact, for the Möbius strip, is a negative twist. and we have the index minus 1 over 2, and then this Riemann-Hilbert operator is invertible. So now let's consider the first class, these torus-like target manifolds. This is our standard example. You have seen it already, prescribed modulus 1. Now we would like to get results, and we need some assumptions, and I call this target manifold admissible when it has a parametrization of this type. These conditions more or less say all target curves are simple, smooth. Smooth means C1 curves, which depend smoothly, again C1, on the boundary point T. So these are very natural assumptions, at least as long as we stay in a C1 theory. So now we have no index of this target manifold, but we have a corresponding number for solutions. We have seen that solutions are lines on this target manifold and the target torus, and they have to go around once in this direction, because here we have the different fibers and we move around the unit socket. So it's clear they have to go around once in this way, but they can wrap around in the other direction. Here we have, this I call the winding number of the solution about the target manifold. And this winding number is 0 in the left example, and it is 2 in the right example. Okay? So, and we will need another assumption, namely the simplest case is that we make the additional assumption that the origin lies in the interior of all target curves. This will play a more important role in the second part of the talk in the afternoon. Then this winding number of W about this target manifold is just a number of zeros in the disk. And this can be generalized a bit. Namely, we can assume that there is a holomorphic function which is continuous on the closure of the disk. This is the disk algebra, such that the values of this W naught are always in the interior of the target curve. Then we can somehow shift everything and we end up with the same thing, origin inside the target curves. And this is the main result which was shown by Schneermann under somewhat stronger assumptions. And I had the pleasure to extend it to the assumption we have seen. Namely, any regular admissible torus-like target manifold is covered by the traces of the fundamental solutions, and the fundamental solutions are those which have winding number 0 about the target manifold. It's covered by these fundamental solutions in the Schlichten. This looks like the picture we have here. This is kind of a natural, say, holomorphic parametrization of the target manifold. So we have a coordinate space, this is the standard torus here. And we have the constant functions as parameter lines, and we have the fibers here as the other parameter lines. And then there is a bijective mapping between this parameter space and the target manifold. Besides the fundamental solutions, there are many other solutions. We can, as we have seen for the Plaschke products, we can prescribe zeros arbitrarily inside, and then we get solutions with higher winding number of all time. So here is the result. If we have 0 inside the target curves and arbitrary fixed points in D, then we get a unique solution. And an additional condition I forgot an additional condition at the boundary for one point. There has to be a fixed value of this solution. Then we get a unique solution which satisfies these additional interpolation conditions and has winding number n. So I think I'm running out of time, so let me skip this. Much more can be said if all target curves are circles. I wanted to skip it, but it does not. And briefly sketch some results about these band-like target manifolds, which comprise the linear problems. Here are some assumptions. Again, we have a parametrization with such a parameter function mu, and this has to be C1. But there's an additional condition number 3, which describes the behavior of these target curves at infinity. In some sense, they have to go in some definite directions. This is a technical condition, but it cannot be completely removed. If we do not put any condition, then the result is getting wrong, which I will show you. So now, again, we have an index. I think this need not to be explained. We have orientable and non-orientable target manifolds, and this is the main result. If the index is negative, then we have at most one solution. And this requires additional conditions. Only in special situations a solution can exist. This is the best case. If this index is 0, then the target manifold is again covered by traces of solutions in such a schlicht manner. And for positive index or non-negative index, we can specify additional interpolation conditions here. And a similar result holds for Riemann-Hilbert problems with non-orientable band-like target manifolds too. Again, these non-orientable cases fit nicely into the gaps between the orientable cases. So I announced that I will also show you some applications. I must confess these are inverse applications. I do not solve real-world problems, but I'm looking for problems which have some physical background, say, and which can be modeled and hopefully also solved using this Riemann-Hilbert technique. So what we are considering, this is a plane potential flow past a porous cylindrical shell. So here we have an axis of such a cylinder, and the flow comes from the left side to the right side. It's planar, and basically it has to go around the cylinder, but the cylinder is just a shell which is porous, so that part of the fluid can penetrate through the surface of the cylinder. So here you see a cross section. So in all cross sections, the flow is the same. And how this fluid goes through the shell, this is controlled by a filtration law. This filtration law establishes a connection between the pressure inside the cylinder at the corresponding boundary point and the pressure outside. And it says that the normal component of the velocity is a function of this pressure difference outside and inside. This can be a linear law or it can be a non-linear law. It's quite general. So what do we have? We have a velocity at infinity. We have some pressure at infinity. This is prescribed. And we also will prescribe a circulation around this cylinder, which, as for a non-permeable cylinder, for a full cylinder, cannot be determined from the model. It must somehow come from the exterior flow. So, and one of the possible problems is to find the pressure distribution inside this hollow cylinder and the velocity field outside. There are different models which go back to the paper of Prof, and the simplest model is to assume that the pressure inside the cylinder is constant. So let's say the fluid somehow goes away and it's just an empty cylinder with a constant pressure filled with air or so. And we can also model potential flow inside the cylinder. So, how to transform this to a Riemann-Hilbert problem? Aha. I will show it in the end. We introduce the velocity potential, which is a harmonic function in the exterior of the cylinder. And you know, the velocity, then the derivatives are the velocity components. We can eliminate the pressure from the filtration law here by Bernoulli's equation. And we end up with a nonlinear boundary value problem for harmonic functions. So we have the normal derivative, which is a function of the derivatives with respect to x and y. Modulus of the gradient. So, and this is a nonlinear version of what is sometimes called an oblique derivative problem for harmonic functions, where we have given coefficients for the derivatives with respect to x and y, and some right-hand side. So we have a nonlinear oblique derivative problem for harmonic functions. And all these problems can be modeled directly as Riemann-Hilbert problems. So all what I'm saying about Riemann-Hilbert problems is also valid for these nonlinear oblique derivative problems for holomorphic functions. So here is the relation. We combine the derivatives to a complex function u plus iv. This is holomorphic, and we end up with a nonlinear Riemann-Hilbert. Okay, so these are the given data, and we have to find these three things: the flux through the cylinder, the velocity field in the exterior domain, and the pressure distribution inside. Yeah, now it's getting technical. I skip all this. We have to examine the shape of these target curves, and this depends on the growth of this filtration law. Interestingly, it changes for if we admit such power laws with an alpha less than 1/2, we get a non-compact target manifold, and if we have this alpha greater than 1/2, it's a compact target manifold. An interesting point is that we get a Riemann-Hilbert problem which depends on an additional parameter. But this can be treated in a similar way as the usual Riemann-Hilbert problems, and we could prove that unreasonable assumptions, whatever this means, this filtration problem is a unique solution which is physically relevant. It has other solutions too, but they are physically crazy. So here are some pictures. We can solve these Riemann-Hilbert problems also numerically. This is a very challenging thing, and I really would enjoy to discuss these numerical procedures with some of you. So everybody who has some algorithm for conformal mapping is also invited to look at Riemann-Hilbert problems, because they are just a generalization of conformal mapping. But the obstacles, there are much more obstacles, I think, but this is not the subject of this talk. Now, I would really like to discuss this with you. So, what we see here, this is the field of the fluid outside with streamlines, and here we have the pressure. this may be interesting here. We have a relatively high flow and high circulation, and then there's a stagnation point here behind this cylinder. Okay, so this is the last theme which I would like to present. It's an application, pseudo-application, I confess, in what is often called electrochemical machining. So here is the setting. We have a massive block of metal here, and this has to be cut through by an electrochemical process. So we have a tool here on the left-hand side. This acts as a cathode, and this anode here, this is the workpiece, which has to be cut, and the cathode moves through this metal. Due to electrolysis, there appears a gap which is filled with some electrolyte, and we hope that we can somehow get a quasi-stationary situation where this cathode moves at some speed to the right, and this free boundary here moves at the same horizontal speed to the right. So in the end we cut, but the situation looks always the same. What is interesting here is that this is a free boundary problem. Again, there are parameters involved, and depending on which parameters are given and which have to be determined, we can set up several problems. Here's the first one, which I show you. We may have given positions. Go back one slide. So this tool consists of two pieces. One, this is non-isolated here, and there's a second part which is isolated. And we can control the points at which the insulation ends. So these are the 2 points B and C here in this model. And our model says it goes to the left at infinity. So we are not interested in what's going on the left-hand side. It's just a limit situation to make this model consistent to our Riemann-Hilbert problems. So then we, in the first problem, we have given positions of these points B and C, and we are interested in the width of the gap, far away from this. Some call this the overcut. And the second, I think, which would be more interesting if it would be a real problem, if these overcuts are given, this is what we want to have, how do we position these ends of the isolated part? So now we have a harmonic function again in this gap here. And we have different conditions. On the insulated part, the normal derivative is 0. This is here and there. Then we have a given voltage here on this BC, which is set to be 0, just a normalization. And we have another given value U0 on the side of this workpiece. So, and now we have this dynamic boundary condition, namely that this cathode moves towards this workpiece at a constant speed, which determines an erosion rate. So the normal derivative is the electric current, probably, which is acting here. This corresponds to the speed times the cosine of this angle, which is shown here. Okay? Just a geometric condition. So what we get, we apply a standard trick in these free boundary value problem treatment by complex analysis. We map this unknown domain to a standard domain, which is a rectangle here. So we have known boundary conditions on all four sides of this rectangle, but we do not know this conformal mapping, and we can map it further to lead our setting of Riemann-Hilbert problems to the unit disk. The essential thing is that these four conditions are satisfied on this rectangle. One condition here is left. This is an additional condition which we get. And so we finally end up with a Riemann-Hilbert problem on the unit disk for this composition of the two mappings, or the inverse. This is the mapping now from here to there. And here you see it. And there are two types of conditions. One is that this part here has to be mapped on the unknown curve, on the unknown free surface. This is the first condition. And the second condition, this comes from condition number 5, from this dynamic boundary condition, and this is linear now. So what we get is a Riemann-Hilbert problem with two types of target curves. We get a curved target curve, which is the shape of the tool, and we get a linear condition on the lower part of the unit circle. So this looks like the blue curves which you see here. So the shape of the blue curves is on the upper part, is the curved target curves, and on the lower part we have just straight lines. And this is bad because it does not satisfy our conditions. So the target curves do not even depend continuously on the boundary point. There's a jump, and the jump is quite dramatic. But knowing a bit about the behavior of solutions, one can modify these boundary conditions. These are now the red curves, without losing solutions. There's a quite large change in these boundary conditions, but we know what the solutions do. And so we can guarantee that this change does not really change these solutions we are interested in. So, and in the end, we get a nice Riemann-Hilbert problem, but this time with a non-orientable target manifold, which was also interesting to us. If you look at the red curves carefully, you see such a normal vector here, such a small vector, and if you go around, then you see starting from here, it turns left, more or less, and then it goes down, 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 and here you end up on the other side. So it's non-orientable, but we know how to treat these problems, and then we can also solve the problem numerically. And what you see here, this is a visualization of the solution. The colors indicate the strength of the electric field. It's high here near these endpoints of the isolated part. And yeah. So it looks. Yeah. This is the end of the first part. Thank you so much.
Thank you. Thank you very much, Elias, for a very nice talk. Questions, comments?
No question. In your last problem, you don't consider inertial effects.
No.
So it's basically snap.
Yeah, this is a simple.
And another thing,
simple,
it looks like it's highly like fluid analogy. It's not really solid because otherwise you'll have stresses, displacement.
Yeah, no.
So it's like fluid.
This is not considered, as I said, it's more or less an inverse application.
Right.
It's
High speed.
not a real life application.
Like jet analogy.
Yeah.
I was wondering, how do you establish well poses for this problem? Via singular integral methods, or?
No, I mean, maybe I can go back to one of the first slides. How do we do? Oh, I did not even make this large. I forgot to make this. Yeah, sorry. You had to look sometime. That. In fact, in the beginning, this problem was considered as a subject of singular integral equations. So Hilbert was the one who introduced the Hilbert operator, which is a singular integral operator. Noether continued in this style, and also Mr. Schwili, Wegerer. They used heavily the techniques from singular integral equations. And also in this development about nonlinear Riemann-Hilbert problems. In the first years, everybody tried to extend the singular integral equation techniques to nonlinear problems. But this has some limitations. And it changed to some extent in 1972, where more and more where the first geometric objects came into consideration. And so I would say today this is a problem of geometric function theory, geometric complex analysis. And Riemann and singular integral equations are still somewhere in the background. But as I will show in the second part of the talk in the afternoon, it can be stated without singular integral equations, totally without.
Other questions, comments? Somebody?
Typically, when you have jump between Neumann to Richter condition, it's useful sometimes to map it. For instance, into some, you keep an angle at right angle.
Yeah.
So, for instance, in your case, you could have mapped it to the region which is the upper half of the angular region.
This is basically what we do in this transformation later. So these jumps and these corners, they are removed by special transformations, and this is exactly what you already
Okay.
If you move in the list of problems from the left to the right, to understand right that the geometric setup then will be higher dimensional, the target manifolds and the ambient space, and
Yes.
Is it
Yes.
completely open, or
it's not completely open, but one cannot expect such nice results, and the problem is getting much more difficult. So in the second part of the talk, I think I will also speak a little bit about these nonlinear transmission conditions. And already these problems are more complicated than the linear problem. The reason is, if you have a general function f here, and just linearize this problem, then you do not only get a condition of this type, but you have to add something like this one. So the conjugate. And this makes things really much more complicated than for the boundary value problem. So I will show some results in the afternoon.
Does your geometric picture of the index and so forth extend to higher connectivity?
To higher connectivity, yeah. So you would have several such target manifolds in extent, yeah. And you can look at these separately, and then you see what's going on one boundary and on the other boundary.
Other questions, comments? Well, yes.
Just a quick one. So I'm just curious about Riemann's thinking when he was posing these problems, especially the ones with the shift in them. So he's got this omega and the omega of alpha at t.
Yeah.
Was he motivated by physical problems or just abstract notion of what he could think about possibly solving?
Yes. I think at this time he was not motivated by physical problems at all. I mean, he was very young still. He was 25 when he wrote his thesis. So he had just some, say, fantasies, very clever and very deep ideas about complex functions. It's unbelievable somehow.
Yeah, regarding the point that Hilbert missed, was that because he wasn't thinking geometrically? He liked his formulae too much, did he?
In fact, Hilbert made a very, very bad and very simple mistake.
All right, I guess we are all looking forward to the continuation in the afternoon. Let's give Elias another round.